Here we have a problem from the AIME 2013 math contest, and it asks us to find how many 5-digit numbers n exist such that 5 divides n, 5 divides the sum of the digits of n, and n has the same first and last digit. I really like these kinds of number theory problems. I think they're really interesting. So let's go ahead and start the solution. First, we want to split n up into the digits. I'll call them A, B, C, D, and F. And I'll go ahead and put a note here in orange that says they are all digits. And that reminds us that all of these numbers are between 0 and 9, or equal to 0 and 9. So A is equal to F. We know that by this last constraint here, that the first digit of n is equal to the last digit of n. We also know that A plus B plus C plus D plus F is equal to 5k, where k is an integer. And lastly, we know that 5 divides n, which means that f is either 0 or 5. We know that because any number that is divisible by 5, as the requirement states, ends in either a 5 or a 0, depending on whether that 5 that divides it is multiplied by an even or an odd number. Okay, but that means that a is either 0 or 5 as well. And if f equals 0, a equals 0, that's pretty self-explanatory by this point here. But now I've left a little note here, because if both a and f are 0, that means we'd have a 0 as our first digit, which means the number wouldn't be a 4-digit number. So I've said here that when both numbers are equal to 0, we have a number that is not 5 digits. So let's only work in the case that both are equal to 5. So we'll have 5 plus b plus c plus d plus 5 equals 5k, where k is still an integer. But then we can subtract 10 from both sides and get b plus c plus d equals 5, we'll say m, where m is just a different integer that we've absorbed these two copies of 5 into. But now we can let b be free as a digit, which means it's between 0 and 9. But if b is free, then c plus d have to complement b in some way. That means we can also set c to be free and just let d be the complement. But if d is the complement, then any combination we take from b and c will end up with only two possibilities for d. If we take both b and c to be 0, then d has to be either 0 or 5. If we take b to be 0 and c to be 1, that means they add to 1, which means that b has to be 4 or 9, so that when you add 1 to 4, you get 5, or you add 1 to 9, you get 10, or a 0 in the 1's place, which is what we're looking for here. So that means that d can be one of two elements for every pair that we have b and c. So that means we have 10 options for b, 10 options for c, and then a remaining 2 options for d. But that means we have 10 times 10 times 2 numbers available when both a and f are 5 that satisfy these requirements. So our answer is 200 numbers satisfy these conditions. And that's enough for now.